Okay, so last time we finished up to number 12. Now we're on 13. This is on 6.5. And so for this one, the secant x, you want to know your vertical asymptotes on the interval from negative 2 pi to 2 pi, including those endpoints. And remember on this, you can use your unit circle packet, which has this paper for sine and cosine, and on the back, you'd have it for secant. The asymptotes are where they're undefined. Okay? So on our problem, it says from negative 2 pi to 2 pi, and so we don't put negative 5 pi halves, because that would be outside of our interval. But we do put basically the plus and minus 3 pi halves and the plus and minus pi halves. So this would be plus and minus 3 pi halves and plus and minus pi halves. Number 14, cosecant x, and you again want to know your vertical asymptotes on that same interval. So for cosecant, we'd look at negative 2 pi, negative pi, 0, pi, 2 pi. So we're going to put 0, plus and minus pi, plus and minus 2 pi. So make sure you put all of that so you know what function it corresponds to. On 15, you have tan x, and you want the vertical asymptotes. Remember that the tangent graph basically looks like this, and your asymptotes would be at negative pi halves and pi halves. And also from plus and minus 3 pi halves. So basically, I'm going to start by saying it's the same as secant x, and then it's plus and minus 3 pi halves and plus and minus pi halves. Same as the secant. Tangent is same as the secant. Okay. So then cotangent x, vertical asymptotes, would be the same as cosecant. CSCX. So that's the 0, plus and minus pi, and plus and minus 2 pi. Cotangent is the same as cosecant. Okay. It's also important for you to remember about the period when we're graphing these. The tangent period is pi. And so they're showing from negative pi halves to pi halves, so it's basically from asymptote to asymptote. And it's the same thing, or same distance for cotangent, but it's from 0 to pi instead. Okay, so those have period pi. But on secant, it basically reflects across pi, and it reflects across 0. Reflects across 0 and pi and 2 pi. So what I mean by that is it'd be the same on the left and right. So even though, like in your drawing, it just looks like it's the right side of it, if you graphed it on the calculator, it wouldn't stop there. So like this is the one for cosecant, which looks like it's like continuous, and this is the one for secant. So SEC X looks like that. So just based on your window, you may see part of one, but not all of it. So it really does continue. Just they're showing from 0 to 2 pi. So the other thing is these two, since they're reciprocals of cosine and sine, these have period 2 pi. So both have period 2 pi.
Is there one that doesn't have it?
Yeah, what I went over here, the period was pi.
Oh, right.
Yeah, period is pi for tan and cotan.
Got it.
Okay, so the rest of the problems are basically on your graph paper. So let's work on those. Let me pause that again. All right, so again, the rest of them are on graph paper. This one's number 18, which is y equals -2 tan x. So what we're going to do is we're going to write a lot of characteristics about them, and then we're also going to put the domain and range.
Wait, can we just write this on the paper?
Yeah, you can put that on the graph paper also. Yeah. I tore mine out because I have mine in my, this composition book. Okay, so y equal -2 tan x. Your characteristics are that it reflects the x-axis because it has a minus sign in front. Your amplitude would be the absolute value of -2, so that's 2. And when it comes to tan and cotan, that has to do with your vertical stretch. That's your vertical stretch. And then as far as your x-intercept, we don't change the period at all because our W is 1. Let me just put this in the middle. The W is 1 and your period is pi like normal. And so that means our x-intercepts are going to be 0, plus and minus pi, and plus and minus 2 pi. And let's see, what else? Our vertical asymptotes would be the middle of those, which would be plus and minus 3 pi halves and plus and minus pi halves. Okay, so let's graph that. -2 tan x. Okay, so it looks like this, and we want a window from -2 pi to 2 pi. So we go to our window settings, -2 pi to 2 pi, or you could just choose the trig window. It's the same thing. And so it looks like that. So it's sort of like the cotangent graph, except for it still goes through the origin. Let me show you that. The cotangent graph, I'm going to put in red, which is like that. Okay? So it's also a decreasing function. Whenever you have a negative tan, it's going to look like cotan, except for it's still shifted a little bit. And you can also see the difference because of the two. The blue one is steeper because it's a vertical stretch. That means it's straighter if it's like bigger than 1. Okay, so we can also say about our domain, which is required, that it's all reals except odd multiples of pi halves. And just like on the previous assignment, this one would look like 2k minus 1 over 2 times pi. So all reals except for that. All reals except for that. And then your range is going to be all real numbers. So for tan and cotan, your range is all real numbers. Always. Yeah, because if you look at the graph for it, tan just continues up, and cotan, same thing. So if you see tan or cotan, your range would be all real numbers. Okay, so now let's use some of these points and graph it. The x-intercepts are going to be useful. 0, pi, 2 pi, negative 2 pi. Our vertical asymptotes at the halves, basically. Now again, the normal tangent would go up from 0 to pi halves, but this one comes down. And it's just going to do that over and over again. This one, I'm stopping right there at the 2 pi. So that's what it looks like. So that's the negative 2 tan x. Now if I compare this to just like regular negative tan x would be wider. You don't have to draw this one. I'm just going to draw one iteration of it. This is minus tan x, so negative 2 tan x is steeper since it's a vertical stretch. So it's not quite as wide. Any questions? So all we really care about, for the most part, are the x-intercepts and the asymptotes, but do try to make it look a little steeper than a regular one would. Okay, so there's 18. Looks like y'all are done writing that. Okay, the next one we have 22. So this one we have y equal tan of 1/2 x. So in this case our w is 1/2. So our period would be pi divided by 1/2, which is 2 pi. So our normal period, like I said earlier, is pi for tan and cotan. And this one goes through the origin, and so our asymptotes are going to be at negative pi and pi. So vertical asymptotes at x equal plus and minus pi k. And your domain would look like all reals x not plus and minus pi k. And your range would just be all reals. The k is the integer, like you saw on the other one. Like if we plug in a 0 for it, it would be at 0. Oh, did I do this? The period is 2 pi for this one. Okay, so it's basically at negative pi and pi.
That's what the periods are?
That's where the asymptotes are. That's where the dashed lines are.
Is that when we have dots of 3 pi half?
Yes. Yeah. Wait. This one's a little different than you might be thinking because of the period being wider. Let's see. The dot would have to be at 2 pi and at negative 2 pi. Okay, let's graph it on the calculator and check it out. Okay, so let's get rid of our first function. Tan 0.5x. Okay, so there's the graph, and if you see 2 pi is our furthest part, pi is in the middle, and that's where our asymptote is. Okay, so basically it's going to go up like that. Tan is an increasing function. Now, I want to be completely 100% accurate on this. The vertical asymptote at plus and minus pi k is true, except for not at k equals 0. So, not k equals 0. Because if it were 0, then that's going to be an x-intercept instead. But it works at 1 pi, 2 pi, 3 pi, 4 pi, and all the negatives. Okay? All right, so that's 22. Okay, 26. This one has to do with the cosecant graph. We have y equal 1/2 CSC x. CSC is cosecant. Bless you. So our amplitude is 1/2. So what we're going to do is change our scale. Instead of counting by ones, we're going to count by halves. So this would be 0.5 and then 1 and then 1.5. And I'll do the negatives down here. Okay, so since this is the one that relates to sine, then it's gonna be odd, and it goes across the origin. It reflects to the origin. So at the pi halves, you put your point here. Our asymptotes are going to be at negative pi and negative 2 pi. And it's a complete up and down cycle, so it's going to be like this and this for one cycle. So this would be considered 1 period worth. 1 period, which is equal to 2 pi. What's that? Okay. I was starting to draw my P here, but I got off the page because I drew it too low. But yeah. So 1 period is 2 pi for that. And then on this one, it's going to just be in front. And asymptote here and there. Okay. So let's write out our descriptions also. Our vertical asymptotes are at x equal 0 plus and minus pi plus and minus 2 pi. Now on Math Excel, they have this worded a little bit different. They have the symbol like this, which means member of or belongs to. It's kind of like a weird E, member of or belongs to. And then it means J for integers. They don't use I, probably because I is reserved for imaginary numbers. So what you're going to see is your domain would be x equal plus and minus k pi, where k belongs to J. K is a member of the integers. Integers being positive and negative whole numbers. And the other part of this is about your range. It's from like here up and from here down. So the range would be from negative infinity, comma, negative 0.5. Then you need a bracket because it includes that number. So anything low up to negative 0.5, union, bracket, 0.5, comma, infinity. The infinities always have parentheses. And on secant and cosecant, because it actually touches that point, you're going to have brackets for the minimums and maximums. So that's what we want. Again, if you want to do this on your calculator as well, you can. This would be the point where it would look like 1.57 something, comma 0.5, which is really pi halves, comma 0.5. So let me show you that. 0.5 cosecant x. Okay, and what I'm going to do is I'm going to go to my minimum, because I'm going to do this one. If I was to do my maximum, it would have been this one or this one. Okay, that's just common sense, but anyway. Analyze graph, go to minimum, and it's a minimum between here and here, which shows you this ordered pair I was talking about. We show a lot of decimal places on our graph, so that's the 1.57 with a bunch of other stuff, which is equivalent to pi halves. And then your y value is 0.5. Any questions? Okay, so there's 26. Now we have 30. This one's pretty similar to it. It's y equal 1/2 cosecant of 2x. So again, our amplitude is 1/2. By the way, I'm just going to write it here that I use 0.5 instead. It's the same thing. It doesn't matter. And you know your w is 2 because it's the number in front of x. Your period is your normal period divided by w. Since we're dealing with cosecant, your normal period would be 2 pi. So we're doing 2 pi divided by 2, which is pi. So your period is not quite as wide. So that means we're going to have more minimums and maximums. Okay, so let's graph that. All I have to do is change this to be a 2 in front, and it looks like that. So we have a vertical asymptote at 0, and then our period is pi. So this is going from negative pi halves to pi halves. Remember, if you want to use your table, do Control T and change your settings. Start it at 0 and then step by pi halves, or if you want to change it to ASC, you can. So pi halves are all your undefined parts. If you wanted to see the other parts for your maximums and minimums, you would have had to use pi fourths. And so there's the negative 0.5, here's the positive 0.5. Now notice again, like what we saw before one time, if you have e to a positive number, that means infinity. And so that's where it's undefined. So this e to a positive number means infinity. So let's go with the vertical asymptote at x equal plus and minus pi halves, plus and minus 3 pi halves, and it's also at 0 and pi.
Not a plus and minus pi?
Oh, yeah, it is. You're right. Good. So this one's going to have a lot more asymptotes than tan or cotan because, as I said a moment ago, there's an up and down cycle that has an asymptote in between. Sort of like you put a dot here, and let's see, our part is going to be 0.5 still. Negative 0.5, negative 1, negative 1.5. And so at this one, it's going to be down. So in other words, this is 1 period worth, which is equal to pi in this case, because it's an up and down cycle. That's how you can think of it. It's not just like from asymptote to asymptote because of the down part. I don't want to over-explain it, but this would be 1 complete period worth right there. Any questions? Then this one goes in the middle. It's down. And this one can't be up because this one was up, so it's down here. You just got to figure out your pattern.
I didn't know which one.
Well, how I look at it is on the graph, to the right of the origin is up, and to the left of the origin is down. And then you just have your repeating pattern. So this one would be up, and so forth. This one would be down, and then this one would be up. So you just have a repeating pattern. Okay, other things we need to write on this one. Let's see. Your minimum is this point, which is pi force, comma 0.5, and it's also this point, which has a 0.5, and this one. So those are all your minimums, and your maximum points would be at your between pi halves and pi. If we think of this as 2 pi force, then this one would be 3 pi force. 3 pi force, comma, negative 0.5. Those are your maximums. Anything with a negative 0.5. Okay, so the domain is all reals, x not equal to k pi halves, so k times pi halves, and then your range would be anything up to negative 0.5. So we have negative infinity, negative 0.5, bracket, union, bracket 0.5 infinity. So again, make sure you have all this other writing with it, especially the domain and range. Okay, so 34. This one is y equal 2 cotan x minus 1. If you want to put parentheses to make sure you're right, your parentheses would go around the x, not around the negative 1. So what that means is when I'm graphing it, I've got to go to the right and then put negative 1. Like that. Okay, so what we know about cotangent, about this function, is our amplitude is 2. It would be a vertical stretch. It's decreasing. And because of this negative 1, your middle, or what's called the point of inflection on these graphs for tan and cotan, it's called the point of inflection, where it changes direction. This happens at all the points where it's y equal negative 1. So let me show you what I mean. We've got 1, 2, 3, negative 1, negative 2, negative 3. At negative 1 is going to be our middle, like that. And it's a cotan graph, which means you have an asymptote at 0. Let's see, our period, or this is pi. So at pi, at 2 pi, negative 2 pi. So you'd have vertical asymptotes at x equals 0, plus and minus pi, plus and minus 2 pi. So that means our domain would be all reals x naught k pi. Again, where k belongs to j, the integers. And remember, anytime it's tan or cotan, you'd have range that's all real numbers. All the 0, pi, 2 pi, negative 2 pi. So all reals x naught k pi. But then your range is all real numbers. So normally for cotangent, our point would be up here, but in this case, because we went down 1, we're at this point. And this is going to be our point of inflection at pi halves, comma, negative 1. So it's going to go like this. And it doesn't alternate, it just keeps on doing that over and over again. Because of that 2, it's a little steeper than before, like on a regular one. So The W on this one would be 1 if you need that for your Math Excel. There's no number in front of X, so your W is 1. And then your period would be pi.
What did you say the range was?
All real numbers. So cosecant and secant have a break in it, but tan and cotan don't. When we're thinking about the range, it's like from the low point to the high point, and there's no horizontal break. I know I put a dashed line here, but that's just for your middle line. It's still actually defined right there. So your range is all real numbers. Bless you. Okay, our last one, number 38. By the way, one quick thing is if you had the other type calculator, if you had a TI 84 plus or 83 plus, you'd have to say 1 over tan instead of cotan. But your calculators have cotan built in, but if you don't, then you'd have to use 1 over tan. Okay? All right. Again, our last one, number 38. This one is y equal 3 cotan a half x minus 2. 3 cotan a half x minus 2. So our amplitude is 3. Negative 2 is where we're going to have a middle line. Let's see, our W is 1/2. So that means our period would be our normal period divided by W, which would have to be pi over 1/2. Remember, for tan and cotan, your normal period is pi. So in this case, you would get 2 pi for your period. Okay, so I'm changing my graph. This will be 3 instead of 2. 3 cotan, and it's a half x. I'm going to put 0.5, and I need to change this to minus 2. Okay, so it's basically going to look like this. The ordered pair that's listed is not very useful. I'm just going to ignore that. The negative 0.346, that was not needed. So what we have is our vertical asymptote at 0 and at 2 pi and negative 2 pi. So vertical asymptote x equals 0 and plus or minus 2 pi. So what that means is your domain is all reals except x not equal to 2 pi k, including 0, because if you put 0 in, it would work. Your domain is all reals except x not 2 pi k. And then your range would be all reals. Okay, so we need to go to pi negative 2. That's our point of inflection. And it's a 3 in front, so it's going to be steep. And then go to negative pi negative 2. And again, it's going to be steep. Okay, so that's the end of the assignment. Now you can work on your Math Excel and your worksheet.